All right, welcome back. And I just recorded for about 20 minutes, never realizing that I wasn't showing you my screen. It was just this page. All right. So I've already written some code. I will show you what I've written. And we'll try to fix some of the stuff I was getting. Syntax errors anyway, so I've got to fix them. What's on the docket for today? Well, we need to execute the program. That is, remember, we're starting off with the script. We've got Flex tokenizing it, feeding it into Bison, which is parsing it into patterns and spitting out an abstract syntax tree. Now, and we've taken the abstract syntax tree and compiled it to a bytecode. And now we need to take that bytecode and execute it. And how do we do that? We write our own little virtual machine to do it. And it sounds really big and fancy, but all that a virtual machine is, in this case, we're emulating it, is just a loop that goes through and says, okay, I'm going to execute this command, loop through again, execute this command. So it's rather straightforward. In order to do this, though, we've got to create a couple classes, and that's where I had messed up. That is, I wasn't showing you the screen. So let's try to do this and do this right. So where are we? Let me just back up. This has a syntax error, and I know it's because I'm changing how I'm doing this right from the get-go. So first of all, let's just say there we go. Okay, so what do we have? I needed we've got this program execute. We don't want that there. We're going to have it down here. And I said it was going to be return a computed expression, but it's not. What we are, however, going to return is ourselves. Return this. Okay, so the idea is that when we call this execute, we're going to do whatever, and then we return ourselves so that we can chain something. Basically, I want to be able to, this is not where it's supposed to go. I'm just trying to show you example code. I want to be able to say that there is, what do we say? TPT base, institute that, and then compile script, and then something 3, that would work, and that will return a program, and then execute it, and then dot out, and that would be a string. You know, again, just being able to chain things along. Would you do that practically speaking? Maybe not, but it helps when you're testing to be able to have that structure. But anyway, okay, so that's what we're doing. Yeah. So program needs to return itself. Okay. Now, so I had it here, but I'm going to remove that. Execute the program's bytecode and no, not in return. Yeah, we'll say that. Return. Okay. I like that. Now, I created a file called computed expression. And if we look at it, first of all, you know what? I need to show you this anyway. At the beginning, there should be at file, and this just tells Doxygen that this is a file that you need to be tracking. And then for the class documentation, we can say executed. There we go. Do I want to do the destructor? I don't think so. Not at the moment. How about computed expression integer? Yes. We will say an integer. And that is the result of a computation. There we go. And this is the there we go, and it takes a param called val, and that is the integer value to be, I want to say represented, but that doesn't quite sound right. I could say the integer value from which to create the blah, 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 whatever. It's the number, it's the value of it to be stored. Or the integer value, that's it. I don't like it, it's too short. That's fine. There we go. So that's all the documentation that we would use. Had to include cstandard int so that it would recognize int64t. And still not liking stuff. I know that. I think 4. This is the computed expression.hpp. So far, all that we're doing is we take in the value and we just assign it to the val. Very, very, very simple. I created, you can see it here. That's ugly. But this is to compile the computed expression.o, and then I put computed expression.o as a in lib object. So, okay, that should work. And now I need to address my syntax errors, and that's over here. So no declaration matches Tang program ampersand Tang program execute. So let's go back to our program.hpp is 2 and cpp is 1. So this is program ampersand compute. Oh, because it's not compute, it's execute. Okay, so it's compiling. It's not doing anything. We're not actually executing anything. but we are getting, it's compiling. Okay, so we know that there's those syntax errors, at least. Now, what do we need? What do we need our program to do? And that's in the program, when the execute is happening. So we're returning ourself. That's fine. What do we? The first thing we need to do is if no, because our bytecode always exists. Our bytecode always exists. So we need our program counter can be, because we're using it as an index into a vector, for that it likes for it to be a type size t. Our program counter, and it's going to start off at 0. That's good. And we're also going to need a stack pointer. That's, should that be 0 or -1? I'm going to check to see what I've done in the past. Almost there, don't worry. You know what? It shouldn't be the okay, for right now we're going to go with the 0. And I know I said stack pointer, but I would really rather use frame pointer. The reason is because later when we get into that's, I think, is that why it's like that? I know. It's like, what are you thinking, Corey? Okay. So I know that we're going to, in order to do recursion, we're going to have to use a stack of other things as well. What do you mean by that? Well, in normal memory, now how it's implemented may differ from system to system, but in general, you've got a stack of memory, and memory is just memory. It doesn't matter. It's just bytes. And you can have a pointer, you can have an integer, you can have whatever. And how the stack, and again, the order that I say this doesn't really matter, but you're going to have like you'll have a reference to kind of where the stack is. Excuse me, the program counter, and then all of your stack variables. on top of it, and then as you do computations, right, the stack may grow and shrink. And then if you need to go into a function, what you're going to do is you're going to pass in like because when the function returns, it needs to know, well, where can I jump back to? So you tell it, hey, yeah, here's where the program counter should go back to. So when it does all of its stuff, and after it's done, the program counter or the next instruction says, okay, what was I pointing to? Oh, okay, there, and it can reset itself. And I know we're going to need all that. The question is do we need that yet? And I'm going to say no. I'm going to say no at the moment. Okay. We will have to have it later, but we should be okay. All right. So we are going to need a vector of, and then this is what we're going to have to change later. But for right now, it's going to be, that should be a C, computed expression pointers. And this is our stack. Yes. Okay. Our program counter is 0, frame pointer is 0, and that. Now, what we would do is we would say while our program counter is less than this bytecode. Is that right? Because I'm doing it differently than I was the other way. So size. So while it's less than that, we're going to go through this loop over and over and over. And what do? We're going to switch, and we've already done this up above, so we need to cast to an opcode this this arrow bytecode PC. So wherever the program counter is. All right. And here's, let's say we have case opcode integer. What do? We have a lot of indent problems. Now, we need to make sure that we earlier used a program check, a dump program check, and this is going to be called the execute program check. Will this work? Yes, it will. Okay. And then we're going to say, we're not going to output anything. We're going to say, if there is, then stack.push back a new computed expression integer with the value of this arrow bytecode PC plus 1, PC plus equals 2, break, Default nothing. Again, I'm not convinced I like my spacing here, but that's fine. That's the switch. That's the while. So what's at the top now of the stack? What I'm going to do is I'm going to say now empty the stack. I will do this. Auto top is stack.back. Now we need to remove this. Or I could just say while stack.size yeah. While the stack.size, okay. That will, oh no, we need to delete everything. So I'm going to say stack.popBack. So this one is saved in top, and now everything else is going to say no, I'm just going to say delete stack.back and then pop the back. And then lastly, program itself should have a result. Is that right? Control B, not control, colon B. Is it 1? No, 2. AST error. I don't have, do I have an optional result? Get AST. I don't, but I'm going to. So let's this is going to be an optional computed expression pointer, and we will call this result. Sure, that works. And now let's go back to this. We will say is equal to top. Unused variable FP. You know what? I'm going to leave that there. All right, let's go. Start at the top. Optional does not name a type. Of course it does. You're supposed to read my mind. See if it likes there. Integer is not a member of Tang opcode. Because I did it in all caps. There, sorry, every once in a while the caps lock. Execute program check does not exist. Well, that's because I haven't written it yet. We're going to copy all of that. And this is maybe safely accessed. This is no longer true, but caps lock. Execute program check, and this is not, well, I mean the first part is, but what do I do as part of that? I need to do more than one thing. For now, I'm just going to say PC is equal to this I need to exit. I can do this. This will not be the prettiest thing that I've done, but it will work. Okay. So it's going to, it'll set the program counter to the size and instantly break, which will break the loop. The loop will clean up itself. this is a to-do, and okay. Push an arrow onto the stack. That's the what we want to do, because right now we're flying really fast and loose with some of our stuff. In fact, we should probably but all I'm going to do at the moment is if okay, so I don't have an error yet. Not return an error. Why am I not doing it right now? Because that's another computed type and we don't have those yet. So set a runtime error. Yes. All right. And if there is something at the top of the stack, save it, delete everything else, and then put that as the result. In fact, I don't even need this error result. The top. I can, this arrow result. That should have only been one. There we go. Again, should still be working. The question is, what's on the stack? So we don't have a way of getting the result, and the problem is we don't want yeah. Okay. We need to add something to program to, just like we've got the get the AST, we need a get result. Will that work? Can we do that? Get result and just stop there? Maybe. right, and this is why? Because we are going to return an option, standard optional. And this is going to be a computed expression. Wow, Corey, you put spaces in everywhere. But this is a pointer to a const computed expression. Yes, I could have put const in between computed expression and the asterisk, and it would have been the same thing. And this is going to get result, and it is a const. And now we need to write this. Of course, the nice thing is I can just yank that and now go to buffer 1, and we're putting it above the execute and the dump bytecode. There we go. And we're just going to that should work. Shouldn't have any problems. Okay, now we can go to our test. I don't think I've opened that. No, I have not. So it'll be 6, buffer 6. Alrighty. Control, not control, :E, and then test cpp. Good. Okay. So we've got our program out. We can dump it. And now, if I call program.execute, it won't do anything. But if program.get result, and that is an optional, so it should return true if it has a value or false if it doesn't. So if it does have one, then I should be able to say cout program dot get result there we go, dereference it, say, Corey, we haven't written that yet. I know, else cout no result. This won't compile yet, but I'm still saving it. Shouldn't compile. Oh, yes. Why? Because it is a pointer. Okay. This is going to look familiar. Just going to call a dump. It's going to say, I don't know what that is. There. Yep, and that is because the computed expression now needs a dump thing. So, computed expression.hpp is 3 and then 4. So we will do this is a virtual standard string dump No, I'm going to give it a default, but I'll do it on the other. Do I need to give it? I might be able to do that. Let's see. Okay, so I obviously need to this is not going to be a delete. This is going to be no, I can't. Okay. It's a virtual, and then this one, oh wait, and it should also be a const. You always put override because, trust me, when you're refactoring stuff, it has saved me a lot of headaches when I thought something was overriding something and it wasn't. Or, yeah, that's okay. And now, buffer before? Sure, why not? Dump const now. I know I want to put all the computed expression ones up top and then put these here, and then what is the fastest way to convert in C++, convert an integer to a string? I think it's just toString. In fact, I'm just not even going to continue looking it up. I'm pretty sure it's to underscore string of this val. And now let's go back to is it 3? Because I'm doing this string thing and I haven't pound included the string. computed expression.cpp. We have virtual standard string dump. Why don't you like this? We're including computed expression, and that has a pound include string. Because I knew I would need that. That's it. It's doing it. What do I mean? Looky here. So this is the AST, abstract syntax tree, integer 3. This is the bytecode. This is the AST that, excuse me, no. This is the computed expression that we get from executing the bytecode. And what it did, that means that we have this command at byte 0, said integer 3, and it pushes this integer onto the stack, and then it's out of instructions. And so it says, well, what's at the top of the stack? I'm going to return that as the result, or I'm going to put that in the optional result thing. And then when we get to our test, I think it's 6. Yes. We say, hey, do we have a result? And so our get result we can see is working. If so, dump it, dump the output, and our dump says that it is just a 3. And that's it. We have a virtual machine. It is so simple, it only has one command. Just push integers onto the stack. Can we test a different number? Yeah, we can. 42. Why not? And it will do a 42. And as I said, I know that it doesn't look the most amazing, but the parts are now here. Now this program.execute is, I mean, technically it could have been called back then. In fact, let's call it then. And it shouldn't change anything. Yes, because when we create the program, it automatically creates the AST and compiles it to bytecode. Does that first. I want to make sure of that. Yep, it parses it. It parses it into the AST, and if the AST exists, then we compile it. What does the parse to? Well, it takes the code into a string stream, creates the scanner, feeds the scanner into the parser, and gives the parser the AST or the error. And we'll do something with the error in just a moment, or probably next time. Well, next 2 or 3. The next 2 or 3 times is going to be making this a little bit more robust and before we start adding expressions. But is specifically we shouldn't be handling raw pointers, because I don't know if you noticed, we created a pointer and we never deleted it. Okay? That's bad. That's a memory leak. We have written a memory leak into here. In fact, let's fix it right now. Okay? When we execute the program, it cleans up everything in the stack except for one thing, and that is what's in the result. So, and where is that being stored? It's being stored on the program. So, 3, no, 2, we have program, and I'm going to put this here as the program destructor. I know what the problem is, and that is the rule of 5. I'm just pulling this up. Oh, wait, do I still have... I did have... There, down here. I'll just search here. C++ rule of 5. And just give me the 5. Basically, if you have to create a destructor, and we have to because we're needing to clean up memory, then we actually need to create 5 things. So originally it was the rule of 3. So we created a destructor. That means we also need to create a copy assignment operator and a copy constructor. What happens if I say program is equal to this, and then I create another program as I don't want to copy that AST. Well, and for that matter, not just the AST. Excuse me, not just the... I said AST. AST is one of them I have to worry about because it's a pointer. And then the result is one that I've got to worry about because it is a pointer. So a destructor, copy assignment, and a copy constructor. But now we have move semantics, so we have to do the move constructor and the move assignment operator. So let's just write these. Destructor. And now the copy constructor. That's right. Yeah, copy constructor. I like putting the there. And this is it takes a constant reference to something of the same type, and then a copy assignment operator. And let's see if I can do this from memory. It's been a while. Copy assignment operator. I'm pretty sure it's a program ampersand. I'm going to check it before I move on, but I'm pretty sure that's what it is. Oh wait, it's probably right over here. Yeah, that's it. Well, that sucks. But that's actually what I was about to type, believe it or not. So it's the operator equals, and then you pass in the same thing. It's the const program ampersand program. All right, and now we need the move constructor, And this is going to be, say, Corey, this seems like a lot of work. Yeah, that's why people do other languages that do a lot of this for them. The move constructor is just another constructor, but it takes program and a double ampersand. There we go. And then the move assignment operator. So this is when we get an R value, which means a temporary variable. And all of these have periods. And yes, I'm going to put them, even though those aren't sentences, I'm sorry, that's being consistent. And this is going to be the same thing. It's a program ampersand operator equals, but program double ampersand program. All right, so these are them. And now we need to take care of them really quickly. All right, so let me remind myself of what I've got. I've got a pointer to an AST node and a pointer to the get result. We're not going to solve all of this right this moment. That is, we could, but it's probably going to add another 30 minutes. Why? Because the AST node is a potentially recursive structure. And so that means I need... Well, no, it's not going to create any memory issues right now, but it will in the future. So I would need to create the rule of 5 for the AST nodes. Yeah. But okay, so for right now, we've got result and what are the pointers? Oh, an error is a pointer. I don't think I like that right now. I don't think I like the error being a pointer. You say, Corey, isn't that going to cause problems? No, we'll fix it. So, that's wrong. Should be that. Should compile. But now what's the errors? Well, I mean, we haven't finished writing the things, so... No, okay, I guess I'm not going to do this at the moment. be either way. Control E, no, B. Do I have a destructor? No, I don't, because I just said, hey, we're gonna have to write a destructor, blah blah blah. Okay, so I'm going to put these right up here at the beginning. Sure, why not? Okay. The tilde program. You say, Corey, did you really just put 2 tildes there? Yeah. That one goes away. And this doesn't need to be there. This is the easiest. Give me a sec. I'm trying to remember my shortcuts. And all that we need to do is if this arrow AST, so that if that is points to an AST, we need to that is a pointer. Okay. So, no, that's not how I do that then. It'll be delete star result. Okay. It doesn't like that computed expression has a non-virtual. I know what it's saying. And yes, this will be needed by other types later. So I'm just going to, in fact, All right. Same with AST. I'll fix that in just a moment. Well, I could probably do it now. Does it? I don't have the AST, so include /AST and public E. Okay. Now, let's get back to the just the rule of 5, shall we? Okay, the rule of 5 for program. We've got our destructor. We've got 4 more things to write. Easiest is to just copy them one at a time. So the copy constructor. That was weird. What does it need to do? So I'm copying something. I need the copying. That means I want a copy of everything. So is equal to program.code. This arrow, or what else? We're just copying things over. Now the problem is the AST one is equal to, and we need a new AST node that is a copy of program.ast. We don't have a constructor like this yet, so it's about to complain. This error is equal to because it's an optional. I don't think it's going to like this, actually. Well, that shouldn't have been capitalized. Why did you capitalize that, Corey? Because I messed up. That's why. Okay. We don't know what to do with error, right? Oh, error info is not its name in this incarnation. And I don't have a copy constructor for the computed expression, but that may be the last thing. Is that right? But the problem is the polymorphism. What do I mean by that? I should say. So here's what I'm thinking through. If program result, this is an optional with a pointer to a computed expression. That's fine. We can even say that the result is equal to a new, but the problem is it does need to point to a computed expression, and that's what this will do. But if we dereference program.result and it is a computed expression integer, it's almost that rather than doing it that way, I need to use a virtual function to ask the computed expression to give me a copy of itself. And yeah. I'm going to have to think about this more. So here's what I'm going to do. I'm just going to comment this out. It will leave us in a state where things compile. Still have a slight memory leak if we push it, but that's what we'll focus on solving next time. And like I said, this added 30 minutes and I didn't even fully solve the problem. That's what happens in programming, right? You see a wrinkle or you see a thread, you pull it, and it starts unraveling everything. So rule of 5 is going to be a thing. I realize I only wrote the destructor and the copy constructor, and even it's not done, but I have to solve this problem until I can, in order to finish writing the copy constructor, and then I'll have the other part. So the next video then is definitely going to have to be dealing with this idea of the rule of 5 and making sure that we're taking good care of our memory. And then we can move on to bigger and better things like how are we going to do our memory management of I want to have an object pool and things like that. But again, we've got all these polymorphic things, so it's going to be dealing with template programming and stuff like that. So yeah, it's going to be a little bit of work, but we'll be okay. We'll get there. And I'm going to have to look up to see how Doxygen documentation works for that. Speaking of Doxygen documentation, let's make our docs and see what happens. I bet we... Do I not have one? There we go. we've got, it looks like, yeah, computed expression, that's in here now. Computed expression integer that relies on computed expression. And in our files, we should have, yeah, there's the computed expression.cpp. So, okay. We're getting there. We're getting there. And yeah, I think that will, and we can always check under files for the tang.hpp, does it bring everything in, right? So right now, if we just call in tang base, it looks like it'll call program, which we'll call computed expression. And so maybe we don't need this tang base. I don't know. We'll see. Maybe we should rename tang base to be just tang itself. That may be as well. We'll have to think about it. Okay, that's enough probably for today. I probably driven you crazy with all the sitting there in silence and thinking. And I'm sorry, that's the nature of programming sometime. Y'all are basically my rubber ducks. Google rubber duck debugging, you'll understand. Where I get to explain it to people who aren't even there, and helps me think through my problems. So anyway, having said that, whenever anyone ever watches this, hope you're having a great day. All right. And again, I hope this is somewhat interesting and fun for you. Okay. So, bye.